SwayamPrabha. Digital India. Educated India.
Okay, so in the previous class, I was talking about particle image velocimetry technique. As I mentioned, in this technique, we illuminate the flow with a laser sheet. The flow is seeded with small particles which are assumed to be the flow tracers, and then we capture the images in a very short time interval, and then by analyzing those images we get to measure the velocity of groups of particles. Now, we will see this in somewhat more detail how this is done. But PIV was actually developed for measurement of fluid velocity, that is single phase flow velocity. Okay. So, we will see the basic principles first, and then how do we apply it for multi-phase flows, as we have done it for other techniques. Okay. So, what are the optical setups for PIV? First thing is the tracer particles. So, as in the case of LDV, in this case also the tracer particles must be able to follow the fluid motion. So, this includes typically alumina or glass microspheres. We can also use different oils. So, we can atomize the oils, or we can produce mist of oils, and we can introduce that to the flow. And different types, other types are also used. Next, the light source. How should we illuminate the flow? So, we know that the scattering from the particles depend on various parameters, and the particle size is a very important parameter here. Now, the problem is that if the particle size is too small, then it can be treated as a flow tracer, or we can call that as a seeding particle. But considering that the intensity of the particles is proportional to square of the particle size, so smaller particles wouldn't scatter also enough light. So, if they don't scatter light, how we will capture it? So, this is the reason why typically high power laser source or light source is essential in this case. So, application of lasers comes into picture. So, this is the reason why we should use lasers, and pulsed lasers particularly, because they can give high power. So, usually solid state pulse lasers are used, for example, NID-YAG or NID-YLF lasers. So, what are the features of the lasers? First thing is that it must be, or I should say it is not a stringent requirement, but in a typical PIV setup we use pulsed lasers. So, here you see these lasers are available typically at a frequency of about 10 Hertz. Okay. And we use dual cavity laser, that is actually we need two laser pulses to capture the flow at a short time interval. So, that is why we need to use dual cavity lasers, which means that which will produce two laser beams. Okay. And we also would be able to control the time delay between the two laser pulses. Then, as I said, it should have high energy if the seeding particle size is very small. Then we should be able to control the energy. This can be done. Now, we should be able to control the delay time, the time between the two pulses. We should be able to control it. Now, another very important feature is the pulse duration of each laser beam is about 5 to 10 nanoseconds, each laser beam. So, what does that mean? That means it virtually freezes the flow field, because this type of time scale is much smaller than Kolmogorov scale even in high speed flows. Okay. So, this is a very important requirement, otherwise you will see streaks as I had shown in the previous example. Okay. So, that is why pulsed lasers are used. And the lasers have typically have Gaussian intensity profiles. So, basically here we have two pulsed lasers, each laser pulse duration is few nanoseconds. Okay. So, it is like this. Okay. Now, the camera can be open during that time. So, even if the camera exposure time or the shutter speed is such that the camera opens or the shutter opens for a longer time, you only visualize the flow only when there is a laser shot. You won't be able to see anything without a laser. Why? Because the particles won't scatter light usually. So, if you put the particle, let us say here in this room, you won't be able to see the particles as such, or you won't be able to image them properly. So, but they will be visible only when you have a laser shot. Then typically lasers generates the light as a form of a beam. So, you get basically a beam of light. So, you need to convert that to a sheet. So, that is why laser sheet optics are used. I am not going detail into it. So, this is achieved by using this is the simplest configuration. So, you can use a cylindrical lens and a spherical lens, a combination of this to produce a laser sheet. So, basically this cylindrical lens expands the laser sheet in only in one direction, and then this lens collimates it. While this lens, which is a spherical lens, this also converges it, forming a beam waist. So, basically your imaging area should be here in this zone, because here you produce a very thin sheet. Then imaging system. So, in a typical PIV system where we use double pulse lasers, the CCD camera or charge coupled device or CMOS cameras are used, but they are used in double exposure mode. Double exposure mode means the shutter opens, and so as I had shown earlier, so this is one laser pulse, this is second laser pulse, and this is what is delta T that you can control. But the camera would behave like this. So, the camera shutter opens such that this image is red, then the camera shutter opens again. So, typically the shutter opening for the second time is longer because it needs some time to read both the images. But as I said, the camera opening time does not control the image, rather the laser pulse duration which controls the image. I mean, we can call the image instantaneous because we will see the image of the particles only when the laser pulse exists. Okay. And this duration is very short, while this is of the order of microseconds. So, let us say this is 10 microsecond, this is 100 microsecond, like that, but this duration is very small. Okay. And this shows that we need to synchronize the laser and the camera. Both of them has to be synchronously operated. So, you have to adjust the laser pulse and the camera shutter opening such that whenever you have shutter opening, at that time only you should fire the laser, otherwise you won't be able to capture it. Okay. So, this is usually done using Arduino boards or National Instruments input output modules. Now, some important steps before we start the experiments. So, we need to decide the seeding density properly, means how much of seeding particles we should use in the flow. And next, we need to know the desired spatial resolution. So, the way we analyze the PIV images is the following. So, this is a sample PIV image that you can see. So, in this image you see the image of several small particles. These are all seeding particles. Okay. So, we divide this image into number of interrogation windows like this, and then we have so actually we collect pairs of images corresponding to the short time interval. So, here I am showing the first image. So, similarly you have second image. So, you do this for the second image also, and you try to match the pattern in one of the interrogation windows. So, you consider, let us say, this interrogation window, and you search in the next image where this pattern is matching, and quantitatively it is done by calculating the cross correlation. So, if the cross correlation coefficient is 1, then you have the best match, okay. And otherwise it will not pick up that, okay, or that position, as I will show later. So, we have to ensure that typically, because here we are tracking group of particles, okay. So, we have to make sure that at least 5 to 15 particles are present in each interrogation window. Now, this basically decides the spatial resolution of your PIV measurement. What does that mean? So, essentially you will get PIV vectors like this, which is defined at the center of each interrogation window. So, now this effectively freezes your spatial resolution of velocity measurement, that is how close you can make the velocity measurements. So, the neighboring points, how close they can be. Now, here you see that, okay, this is basically the spatial resolution, means within this distance only you can take measurements. Now, why it is important? Because now imagine this distance is larger than Kolmogorov scale, then you can never resolve Kolmogorov scale in your flow. So, the spatial resolution must be smaller than the time scale of the turbulent eddies that you want to resolve. Now, if this spatial resolution is, say, somewhere between Kolmogorov scale and large eddy scales, then what will happen is that you naturally filter out the small scales. So, inherently you impose a filter, as in the case of LES. But in case of LES, we model the rest. Here there is no modeling. So, basically you will not be able to capture the eddies below the spatial resolution. So, that is the point. And also we need to optimize the time delay between the two laser pulses. If the time delay is too short, then what will happen? You will not see movement of the particles. The particles will not move. Then you will not be able to capture the movement correctly because of the uncertainties. It will be buried in the uncertainty. But if the, on the other hand, if the particle movement is much larger, okay, larger than the interrogation window, then you will not be able to match the pattern ever. Okay. So, this has to be judiciously described, means finalized. Okay. So, this slide shows the image processing algorithm for PIV. So, as I have already told you, so you get basically pairs of images. So, this is one pair of images. So, if you play the two pairs of images right one after the other, you will be able to see small movement of the particles. Okay. So, as I mentioned, so you define an interrogation window here and you define a search window here, and you go on matching this window over this, and you try to see at which location this window matches one part of the search window. Now, let us say you see that this window is matching this part well. This means that this should be the velocity. Okay. And for this matching, we calculate the cross correlation. So, basically you get two-dimensional cross correlation coefficient in a 2D plane as shown here. And here you see that here at this location the cross correlation coefficient is maximum. So, that is picked as the location where this group of particles have moved, and you go on doing that for different interrogation windows, and that is how you get the instantaneous vector field. So, basically in PIV we can measure the fluid velocity vectors at different locations at the same time. So, this is the main difference with respect to LDV. Okay. So, in case of LDV or pitot tube or hot wire anemometer, these are all point measurement techniques where you can get the measurements in spatial measurements, but you can only measure statistics. For example, you will be able to show the mean velocity vector field or the turbulence intensity, but you will not be able to get instantaneous vectors at different location at the same time. So, this is the power of PIV technique. Okay, the classical PIV techniques has been extended also. So, the classical technique is essentially capable of providing us 2D 2C velocity measurement, means two-dimensional, two-component. Now, we can extend that to stereo PIV. Stereo PIV means you have two cameras looking at the flow field. So, instead of one camera, you use two cameras. So, it works the same way as our eyes work. So, our eyes capture, each eye captures two different views, and the views are reconstructed in brain, and that is what gives us the 3D feeling. Okay. And the same thing is done here. So, in this case we can get 2D 3C measurements, which means that the measurements are still obtained in a 2D plane. So, what I am showing here, this is actually one plane, I am showing the top view. So, you have one camera say here and the other camera say here. Both are looking at the same field of view, but we can obtain the third velocity component or Z component we can get. So, apart from X, Y, we can get Z component also. Now, this also has been extended to tomographic PIV. So, in case of tomographic PIV, it is like a numerical simulation. You will get three-dimensional, three-component velocity data, but this requires use of more than two cameras. Typically 4 cameras are used or even more than that, and all the cameras have to be calibrated properly such that all of them look at the same field of view. So, that is why even if this can be done, it is quite tedious, okay, and also the setup is expensive. Now, an extension of conventional PIV is also high speed PIV. High speed PIV means in a conventional PIV, as I said, the rep rate or the repetition rate of the laser is typically 10 hertz, which means that actually you have this scenario. So, 2 laser pulses and this is the delta t time delay, but you have this kind of pairs of laser pulses which are generated corresponding to this 10 hertz. 10 hertz means 0.1 second. So, this is basically 0.1 second. Okay. So, again in in temporal sense, okay, here also you are basically filtering out the turbulent eddies, okay, because you cannot measure anything below this time scale. And if this time scale is longer than the large eddy time scale, I hope you are able to follow it. If this time scale is longer than the large eddy time scales, this would mean that you would capture the flow field in different eddies at different times, which are not correlated. These are uncorrelated measurements, okay, which also can be used to calculate the statistics, okay. But if you want to measure time resolved flow, if you want to resolve the times, the flow, when I say resolve the time, this means that the time period between two velocity vector fields should be less than the time scale of the turbulent eddies. And if you really want to do this to resolve Kolmogorov time scales also, then you have to make it smaller than the Kolmogorov eddies, time scale of the Kolmogorov eddies, okay. So that is why we have to rely on high speed PIV. So this will require use of high speed laser as well as high speed cameras, okay. And there are other extensions like micro PIV, where you want to look at a very small field of view. So you encounter different challenges there. We are not going detail into this. Now, one can note that the advent of PIV was a game changer in advancing our understanding for turbulence. This is mainly because of its ability to measure the velocity field spatially, okay. Now, we should not think that we have the only advantage compared to LDV, that, okay, we can avoid multiple measurements, okay, because you obtain spatial measurements in a plane, you avoid multiple measurements. That is not the only advantage. The main advantage is basically its ability to extract vital turbulent statistics such as 2-point velocity correlation, as I have already explained earlier. So this 2-point velocity correlation is a very important quantity in turbulence, if we want to understand turbulence. That is, at any instant of time, you have measurements here and here, and you try to correlate these two. So you do this for different time, and then you average it. But this requires measurement of the velocity at the same time, but at different locations, okay. So this basically facilitates identification of coherent structures in turbulence. So you can imagine coherent structures as corresponding to the turbulent eddies, okay. And also we can measure eddy size anisotropy within turbulent flows with high spatial resolution, okay. So this is the main advantage. The advantage is not just that we can avoid multiple measurements, okay. It's not only about the time. So you avoid multiple measurements means one can say that, okay, the time that you will need to characterize the flow is less. But the advantage is not only that. The main advantage is its ability to measure turbulence, to provide us turbulence measurements properly. Okay, so now the question is, can we use PIV for measurement of dispersed particles in multiphase flows? So now you have dispersed multiphase flows where you have particles. So now the question is, can we use PIV to measure particle velocity? Let's see. So for example, let's consider measurement of velocity of spray droplets by PIV. So this is a spray by an injector, basically an IC engine injector, okay. And you see how the spray develops with time here, okay. So basically the spray is injected using an injector which pressurizes the liquid to high pressure and then injects the pressurized liquid into ambience. So, that is how they have done, they have captured the images. And now, these authors have performed PIV measurements over this. So, you see you get the velocity vectors, but what is the difference with respect to the previous PIV measurements that I had shown or what we have discussed? In this case, you do not have seeding particles. In this case, you have dispersed particles, which are droplets in this case. So, the velocity that you get here is actually the velocity of the spray. It is not that of the gas flow. That is what you have to remember. Now, but what is the problem here? So, what do we actually measure, or how much meaningful these measurements are? So, now you see that in your interrogation window, instead of seeding particles, you have dispersed particles. But while the size of seeding particles won't matter much, whether it is say 1 micron or 5 micron, it does not matter much. Why? Because we know that the Stokes number is anyway much smaller than 1. So, they are flow tracers. But in case of dispersed particles, that is not the case. Okay. So, we have different particles which may move at different velocity. Okay. Then what will happen in that, in this example, we have many droplets in this interrogation window, but individual droplets have individual velocities. So, but when you do PIV, you get velocity for all these droplets within a measurement interrogation window. So, then the question is, you get some type of droplet size averaged velocity. So, but we do not know this velocity that we get corresponds to which droplet size. We have no information about that, because this is, we are not measuring velocity conditional on size. Okay. So, basically the point is, this is meaningful if the droplet size velocity correlation is not significant, or in other words, the droplet velocity does not vary strongly with size. Okay. So, if that is the case, then you get some meaningful measurements. Okay. So, now the next question is, can we use PIV for measurement of carrier phase in multiphase flows? We have posed the same questions while discussing LDV and PDP. So, what should we do for this purpose? What we can do is that we can add some tracer particles which can provide carrier phase velocity. But what will happen? What are the challenges in this case is that if we just add tracer particles, in your PIV image, you will get both tracer particles as well as your dispersed particles. Both are present. Okay. Now, the issue of crosstalk, if you remember, we had discussed this, comes into picture. Now, if you simply process an interrogation window that has the dispersed particles as well as the tracer particles, let us say you just process it and you will get some velocity field, but that is of no use, because we do not know if that corresponds to particle phase or tracer phase. Actually, it will be more biased towards the particle phase, because particles occupy more space in your window. Okay. So, we have mainly problem if the particle size distribution overlap. Okay. Then also another problem is camera saturation. Camera saturation means, to visualize the small tracer particles, what we do is that we increase the intensity of the laser. But when you do so, the dispersed particles will give also very high intensity, and that will saturate your camera. Saturate your camera means each camera, okay, has some dynamic range. We say, let's say 12-bit camera. So 12-bit camera means the intensity values can range from 0 to 2 to the power of 12. But if the light intensity goes beyond this, then the CCD chip will be damaged or the camera chip will be damaged. So that is called camera saturation. We should always avoid camera saturation whenever we use any camera. So this is a problem. So now if we try to do size or intensity based discrimination between the two phases in the spray PIV image, it is not easy. If we want to discriminate the intensity, the intensity of the tracer particles and intensity of the dispersed particles, it is not easy. Why? Why not easy? If the particle size and seeding particle size nearly overlap. If you have, let's say, 200 micron particles and seeding particles are 1 micron, let's say 10 micron, it does not matter. But still there, imaging both will be challenging of the camera saturation issue. But let's say you avoid that somehow. Even in that case, we can basically, we know which corresponds to dispersed particles, which corresponds to tracers. But if you are typically, let's say you have a spray where you have 10 to 100 micron particles, then it will be very difficult. Why? Because of the Gaussian nature of the light, as we had discussed earlier. Because the laser sheet always has a Gaussian nature, so the small particles which are towards the edge, you won't be able to detect them, while large particles will always be detected. So that is the problem. So now what is the alternate? The alternate is LIF-ME technique. So for dispersed phase measurements. Now what is LIF-ME technique? We'll see. Before that, let's see what is laser-induced fluorescence. So laser-induced fluorescence is basically another technique, another optical diagnostic which is used to visualize and measure the concentration and distribution of certain species in gases or liquids. So in this case, what we do is that we add some dye, or some dye may be naturally present which can fluoresce, and we add some dye to the flow and we excite that with a suitable laser. Then the molecules are excited, okay, and when they relax back to the lower energy state, they emit light. That is what is fluorescence. Okay. But what is interesting here is that the light which is emitted, that the fluorescence light, it has a different wavelength than the incident light. So that is the reason by using a suitable optical filter, you can filter out the incident light or the scattered light, and you capture only the fluorescence light. So that is the basic principle of laser-induced fluorescence technique. So now what can we do in our case? So we can tag the particles with some dyes. Let's consider for the time being liquid particles only. So imagine you have you want to take two-phase measurements in a spray where you have liquid droplets and you also want to measure the gas phase. Okay. So in that case, you can add some dye only to the liquid droplet, okay, but don't add anything to the tracers. Now if you illuminate, so typically let's say if you are working with let's say water spray, you can use rhodamine dye, and if you illuminate that with a green laser, the fluorescence that you will get is around red, or it is red shifted, which means that the fluorescence light is close to orange color. So that is why this is shown as orange color. So now if I keep a filter in front of my camera, then I won't be able to see these tracers because it does not have the dye. I will only see the dispersed particles. So, similarly, I can tag some fluorescence dye to the tracers instead of the particles. In that case, using same approach, we can capture the tracer particles. So, the dispersed particles are automatically filtered out in your image. So, that is the basic principle of leaf-me PIV technique. I hope this is clear. So, we can separate the phases in the post processing also. So, this is an example here you see. So, in this case the dye is added to the dispersed particles. So, now here you see two cameras are used. Now, by putting a filter in front of one camera, we capture only inherently we capture the dispersed particles only. On the other hand, in this camera we capture both. However, because we know the position of the particles here, we can subtract it in the post processing part, and such that these are all removed, and what you get is the seeding particles. So, this is how we separate the particles and the seeding particles. We can do the same thing as I said for tracer particles, tagging the dye to the tracer particles and doing similar approach. Okay. People have tried also many different approaches, for example, using two different dyes, two different lasers. Okay. As shown here in all these examples, I am just briefly showing you how this is done. So, basically, now how do we do image processing of the phase separated PIV images? So, phase separated PIV images means you have the PIV image of the tracer particles. If we consider first the tracer particles image, it has some empty space. Those empty space corresponds to the dispersed particles. We have removed it some way. So, that is why these are non-ideal. Okay. So, that is the reason why straightforward application of the PIV image processing algorithms for such images would give us erroneous results. Okay. How about the image for the tracer particles? So, the dispersed particles. So, you get the image of the dispersed particles, say like this. Then what we can do here, if the loading is dilute, it is not dense, then we can track individual particles, because in this case also you have a pair of images. Whenever we say PIV, this means that you must have a pair of images separated by a definite short time interval. So, in the next image, you have these particles moving to a different location. Now, we can, because the loading is less or the number of particles are less, we can track individual particles and get individual particle velocity, and this is known as particle tracking velocity. Okay. So, in this case, we can get velocity of individual particles, not group of particles. But on the other hand, you have the tracer image which is devoid of the dispersed particles, you have to process it some way. So, different image processing techniques have been developed to account for such kind of non-ideal PIV images. For example, here you see this image, this is such an image where actually these particles appear and we have filtered out, and in this case a mask is created, and somehow this mask is used during the PIV image processing to improve accuracy. Okay. We are not going detail into it, I thought I will just show you how this is done. So, for instance, if you have, so this is the ideal case and this is the non-ideal case. So, here we have removed some particles that possibly you won't be able to see here. And now if you process this image, you get a sharp correlation peak as shown here. So this gives you a good velocity vector field. But if you process this, that peak is gone, because in your interrogation window now you have empty spaces or holes. So by accounting that in the masks, we can again regain the correlation peak. So this is the reason why the image processing has to be modified. One approach is this masking technique. So there are challenges in LIF PIV approach, although the in principle it sounds quite promising. That is, you add some fluorescence dye either to the dispersed particles or to the tracers or both, and use it to separate the two phases. However, there are many other challenges. For example, transmission efficiency of filters, the filters that you use, it's never it cannot block always all the scattered light. So some spectral leakage happens. Okay. And there are also uncertainty in processing the images. Okay. So then the question is, if LIF PIV image has these challenges, and obviously these challenges are amplified if your volume fraction or mass loading of the particle phase goes up. So if you have more particles, then you have more challenges, especially when you have a scenario where you have two-way coupling between the two phases. Okay, that these techniques won't work there. Okay, because the loading is already high there. Because mostly you will have particles, and then forget about the case where we have collision and coalescence, where we have really high loading. So these techniques mostly work for dilute loading cases. Okay. But they provide valuable information. Okay. So LIF PIV approach, for if we only restrict to dilute loading, the advantage is that we can get two-phase measurement. It is possible with good accuracy. But the problem is that PIV cannot give, or it cannot provide particle size. So what you measure is basically particle velocity and fluid velocity, but you don't know particle size. So if particle size is not known, okay, then the results may not be meaningful. Okay. You may wonder why particle size is not known. If we have this kind of images, we can find the particle size also. But actually this is not true. This is only a kind of an example image. So the it is means processing these kind of images, either LIF image or mean scattering images, to measure particle size is always it is always associated with high inaccuracy because of different reasons, especially when you are measuring particles around 100 micron or of that order or below or of that order. Okay. So that is why particle size information is also important. So now what do we do? Is there any technique which can provide that? So yes, so there are other techniques which can provide that information, that we measure particle size, particle velocity, as well as tracer velocity or carrier phase velocity, that we will see in the next class.